Welcome to the deep dive. Today, we're doing more than just scratching the surface. We are really plunging deep into something foundational in Java, the map collection.
That's right.
Forget endlessly searching through simple lists, maps. They just completely change how your code finds and organizes information. It's like giving your data a super efficient brain.
Yeah, a brain is a good way to put it.
So, our mission today,
Mm-hmm.
equip you with the essential understanding of this really crucial tool, kind of fast track you to feeling comfortable and making smart choices with it. Think of it like your shortcut to handling complex data organization neatly.
Precisely. And it's different from, say, lists or sets, right? The storing of individual items, maybe in order, maybe unique items only.
Right.
But maps work on a completely different idea. They store data as these pairs,
Client.
key-value pairs.
Key-value pairs.
Yeah, and the fundamental thing here is each key, it's absolutely unique, and it's tied directly, linked to one specific value. It's, the difference between just having a list of words and having a dictionary, where each word, that's your unique key, instantly gives you its definition, the value.
Gotcha. Like looking something up.
Exactly. And that structure makes maps just essential for all sorts of things. User profiles, system settings, anything where you need to look data up fast based on some identifier.
Okay, let's unpack that a bit more.
Yeah.
So for anyone who's maybe used dictionaries in Python or associative arrays elsewhere, Java maps, they work on that same basic idea, yeah?
Pretty much, yes.
Yeah.
The core concept is very similar.
So at its heart, you can kind of picture it like a table, maybe two columns. One for these unique IDs, the keys,
The keys.
and the other holds the actual data, the values tied to each key. Like you mentioned a phone book earlier, or maybe like an old Rolodex. Use the name, the key to instantly sign the phone number, the value.
Exactly. And that unique key part, it's absolutely critical. You just cannot have two identical keys in the same map. One key maps to exactly one value.
One key, one value.
Yeah.
Period.
Period. Now, it is okay for different keys to point to the same value. That's fine.
Okay.
So, back to the Rolodex, two different names, two different keys could definitely have the same phone number listed.
Right. Makes sense.
And another thing, generally speaking, maps don't promise to keep things in any specific order, like the order you added them. Some types do, but the basic idea doesn't guarantee it.
Okay.
But the real magic, the genius of it, is how efficient they are. Super fast for finding, adding, or removing data. Why? Because they use those unique keys for direct access. No searching through everything.
That structure, yeah, it sounds incredibly efficient. Okay, but let's get our hands dirty here. We've got this key value power.
Yeah.
What can we actually do with a map in our code? What are the main actions?
Great question. It all revolves around working with those key value pairs. So you can put a new pair in, like associating a unique product ID, the key, with its description and price, the value.
Okay, adding stuff.
Then you can get a value just by giving the key. So you ask the map, hey, what's the value for this product ID?
Retrieving it.
Yep. You can replace an existing value. Say the price changes for that product ID. You update the value linked to that key.
Makes sense. Updates.
Or you can remove a pair entirely. Maybe the product's discontinued. Just take it out.
Okay.
And really importantly, you can check if something's already in there. You can ask contains key or contains value. Does this key exist? Does this value exist anywhere in the map?
Ah, checking existence. That's handy.
Super handy. Imagine like a big inventory system for an online store. Each product has a unique SKU number. That's the key. Linked to all its details, price, stock level, category, whatever. That's the value. You just use the SKU and bam, all the info's right there, ready for you to view or update in real time.
And that bam, that near instant lookup.
Yeah.
Even if you have thousands, millions of products, that's what really sets maps apart, isn't it? Feels almost like, well, magic sometimes.
It really does feel that way. And the secret behind that speed, for most map types anyway, is a technique called hashing.
Hashing. Okay. Heard of it.
Yeah. Now, we don't need to dive into like the super deep algorithmic details today. That's maybe another deep dive.
Okay.
But the basic idea of hashing is it converts your key, whatever it is, into a number. And that number acts like an address or an index inside the map's hidden storage.
Ah, like an internal address book for the keys.
Exactly. It lets the map jump almost directly to the right spot to find the value or to store it. It avoids having to check every single entry one by one. It's like having, an internal GPS for every key.
That's a great analogy, internal GPS.
And one really crucial point to remember, if you try to put a new key value pair, but that key already exists in the map.
What happens then? Does it fail?
No, it just replaces the old value associated with that key with the new value you provided.
Oh, okay, so it updates it automatically.
Yep. That's how it ensures keys stay unique. The newest put for a given key wins. And maps are also really flexible. You can store almost any kind of Java object as your keys or your values. The main thing for keys is they need to work properly with that hashing idea, which means having good hash code and equals methods defined.
Okay, so the map has this internal GPS using hashing.
Mm.
Super efficient. Avoids linear searching. Got it. Now, you mentioned most map types. This is where I think it gets really interesting and maybe a bit complex. Java doesn't just have one map, there are different versions.
Exactly. It's not a one-size-fits-all situation. Java gives you several different map implementations, and each one has its own characteristics, its own strengths and weaknesses.
So choosing the right one actually matters.
Oh, absolutely. Picking the right flavor of map can really affect how your application performs, how it behaves, even subtle things like memory usage.
Okay, let's break them down then. What are the main contenders?
Right. First up, the big one, HashMap. This is like 90% of the time the map you'll probably reach for.
The default choice.
Pretty much. Its main selling point is speed. It's very fast for adding, put, finding, get, and removing entries thanks to that hashing we talked about.
Okay, fast. What's the catch?
The trade-off is it makes absolutely no promises about the order of the keys. If you loop through a hash map, the items might appear in what seems like a random jumble. It's optimized for speed, not order.
Gotcha. No guaranteed order.
Also, it's fairly lenient. It allows you to store one key that is null, and it allows multiple values to be null, which can be useful, but you have to be careful about handling those nulls later.
Right. Could lead to errors if you're not expecting them.
Definitely. So think of HashMap for things like maybe tracking user sessions on a website by session ID. You need fast lookups, but the order doesn't really matter.
Okay, hashmap.fast, no order guarantee, allows some nulls. What if order does matter? What if I need things kept in the sequence I added them?
Good question. That's exactly where LinkedHashMap comes in. Think of it as a hash map with a memory.
A memory.
Yeah. Under the hood, it's still using hashing for speed, like HashMap, but it also maintains an extra structure, a doubly linked list that runs through all the entries.
Okay.
And that linked list keeps track of the order in which you inserted the key value pairs, or, optionally, the order in which they were last accessed.
Oh, interesting. So it remembers the sequence.
Exactly. So when you iterate over a linked hash map, you get the items back in that predictable insertion order or access order. Because it has to manage this extra list, it's usually a tiny bit slower than HashMap for adding and removing things.
A slight performance hit for the order guarantee.
Right, but often worth it if order is important. Like HashMap, it also allows one null key and multiple null values. A classic example is a shopping cart. You want to show the items in the cart in the exact order the user added them, right?
Yeah, absolutely. You wouldn't want them jumbled up.
Linked HashMap is perfect for that. Or maybe caching, where you want to remove the oldest items first. Linked HashMap makes that easy.
That's a really key difference then. Insertion order preserved. Okay, what if I don't care about insertion order, but I need the keys themselves to be sorted, like alphabetically or numerically?
For that specific need, you turn to TreeMap. This one works quite differently. It doesn't use hashing at all.
No hashing. How does it work then?
It stores the keys in a sorted order, either using their natural ordering, like numbers sorting numerically, strings alphabetically, or using a custom comparison logic you provide.
So it keeps them sorted automatically.
Yes. Internally, it uses a special kind of balanced tree structure, usually a red-black tree, to maintain the sorted order efficiently as you add or remove items.
A tree. Okay. Sounds more complex.
It is, a bit. And because it has to maintain that sorted structure constantly, TreeMap is generally slower than HashMap for basic put and get operations. The sorting comes at a performance cost.
Slower than HashMap, but gives you sorted keys.
Correct. And it has a stricter rule about nulls. TreeMap does not allow null keys at all. Trying to add a null key will cause an error. It does, however, allow null values.
No null keys.
Ah.
Got it. So when would I use this?
Think about anything where you need to iterate over the keys in a sorted fashion. A dictionary app displaying words alphabetically, or a leaderboard for a game where you want player scores, the keys maybe, sorted from highest to lowest. TreeMap handles that sorting for you.
Okay, that makes sense. Sorted views of the data. And then there's one more you mentioned, Hashtable. Sounds kind of old.
It is, yeah. Hashtable is the legacy map implementation. You'll definitely see it in older Java code, maybe code written before the modern collections framework really took shape around Java 1.2, Java 2.
So probably not something I should choose for new projects.
Generally, no. It's rarely the best choice for new development. It's typically slower than HashMap.
Slower. Why?
Well, its main distinguishing feature and the reason for its slowness is that all of its methods are synchronized,
Synchronized.
meaning it's inherently thread safe. It's designed to be used safely in situations where multiple threads, like different parts of your program running concurrently, might try to access and modify the map at the same time. Hashtable prevents them from corrupting the data.
Ah, built-in protection for multi-threading.
Yes, but that protection mechanism adds overhead, making it slower even when only one thread is using it. Also, it's much stricter about nulls. Hashtable does not allow null keys or our null values at all.
No nulls allowed, period. And slower because of thread safety.
Exactly. So unless you're working with very old code or have a very specific need for that exact type of built-in synchronization, and often there are better ways now, like concurrent HashMap, you generally avoid Hashtable. You might find it used in old configuration systems or legacy enterprise code.
Wow. Okay. So HashMap for speed, LinkedHashMap for insertion order, TreeMap for sorted keys, and Hashtable for, well, mostly legacy reasons or specific thread safety needs. That's a lot to keep track of.
It is initially.
So let's bring it back to the listener. What does this all mean for you when you're sitting down to write some code? You think, okay, I need a map here. How do you actually pick the right one? It sounds like choosing wrong could, maybe not break things immediately, but cause weird performance issues or unexpected behavior later on.
That's exactly the right way to think about it. You've nailed the core challenge. It really, truly boils down to understanding your specific requirements for that piece of data. What problem are you solving?
Right.
So here's a kind of mental checklist. Do you primarily need the absolute fastest lookups, adds, and removes, and you genuinely don't care about the order?
Yeah.
Use HashMap. That's your default, your workhorse. Think caches, simple lookups like user ID to user object.
Okay, default is HashMap
Unless you need to maintain the order in which items were added. You need to iterate through them later in that same sequence.
like the shopping cart.
Exactly. Or maybe a history of actions or configuration settings read from a file that need to stay in order. Then use LinkedHashMap.
Got it. Order matters, LinkedHashMap.
Right. Or do you need the keys themselves to be automatically sorted, maybe alphabetically, numerically, or by some custom logic you define?
The leaderboard example.
Perfect. Or generating any kind of sorted report based on keys. In that case, use TreeMap. Be mindful it's a bit slower for insert skets.
Sorted keys, TreeMap. Makes sense.
And finally, are you working with really old code that already uses Hashtable? Or do you have a very specific, perhaps legacy-driven need for its built-in method-level thread safety, and performance isn't the absolute top concern? Only then would you consider Hashtable. And even then, you might look at newer alternatives first, like a concurrent HashMap.
So Hashtable is really the exception.
Very much the exception for new code, yes.
That's a super helpful guide. And it sounds like for anyone just, getting started, really digging into maps for the first time.
Start with HashMap. Absolutely. It's the most common, the most versatile. Get comfortable with that one first. It'll cover a huge range of use cases, and you'll learn the core map concepts. Then branch out when you hit a specific need for order or sorting.
Okay, start with HashMap. Good advice. Now, to really nail this down, let's revisit some practical examples. We've mentioned a few, but just to connect the dots again. Besides, say, inventory, think about a simple grocery list app. Item name is the key, quantity is the value. Perfect for quickly finding milk and updating the quantity, or removing eggs. HashMap works great there.
Yep, classic use case.
Or a student database. Student ID is the unique key. The value could be a whole object with their name, grade, courses. You need instant lookup by ID. Again, HashMap is probably fine unless you need ID sorted for some reason.
Right, or maybe application settings. The setting name, like font size, is the key, and the value is 12. You need to fetch settings quickly by name.
Yeah, all great examples.
And just to make sure you're using them effectively, maybe a few more quick tips. First, pick good keys. They need to be unique, obviously. But also think about using immutable objects as keys if possible. Things like string or integer long.
Why immutable?
Because if a key object's internal state changes after you put it in the map, its hash code might change. And if the hash code changes, the map might not be able to find it anymore. It gets lost. Immutables prevent that.
Ah, good point. Avoid keys that change their spots.
Exactly. Second, just be mindful of memory. Maps are great, but they do have some overhead compared to, say, a simple array list because they need to store both keys and values, plus manage that internal structure, like the hash table array. For huge data sets, it's just something to be aware of.
Okay, memory usage.
And finally, especially when you're learning, test. Play around with a small map, add things, remove things, add a duplicate key, and see how the value gets replaced. Really get a feel for how it behaves before you rely on it in a big, complex system.
Sound advice. Test small first.
I mean, I remember way back trying to manage like product variations using just lists. It was a nightmare keeping track of updates. Discovering maps felt like unlocking a superpower. It really shows how choosing the right tool doesn't just affect speed, it simplifies your whole approach to the problem.
Yeah, absolutely. This deep dive, I think, has really highlighted just how powerful and versatile Java's map collection is. It's not just about storing data. It's about organizing it logically, accessing it incredibly quickly. It's a fundamental tool for everything from simple apps to really complex software systems.
Definitely. And hopefully this gives everyone a really solid foundation for understanding and using maps in Java, but the real learning always comes from actually doing it, applying the concepts.
Sure.
So maybe a final thought for everyone listening. Think about a task you do regularly, maybe even outside of coding. Organizing recipes, managing digital photos, tracking books you've read. How could you model that data using a map?
Hmm. Interesting challenge.
And then take it a step further. How would choosing a hash map versus, say, a tree map fundamentally change how you interact with that data? What would be the pros and cons? Thinking through that might reveal some surprising insights about how these different maps really work in practice.